Complex zeros of polynomial functions. The number z is a complex number if z can be written in the form a plus bi, where a and b are real numbers and I is the imaginary number. z1 equals 5 plus 0i is a complex number where a equals 5 and b equals 0. z2 equals 0 plus 2i, and that's a complex number where a equals 0 and b equals 2. Careful, when a equals 0, z equals bi is called a pure imaginary number. Note, the real numbers are a subset of the complex numbers and the pure imaginary numbers are a subset of the complex numbers. I squared equals -1. I equals the square root of -1 only. If x squared equals m, then x equals plus or minus the square root of m. Consider the quadratic equation. Ax squared plus bx plus c equals 0. If the discriminant b squared minus 4ac is less than 0, then the complex solutions to the equation are x 1 and 2 equal -b over 2a plus or minus the square root of the absolute value of b squared minus 4ac over 2a times I. A complex root or complex zero of a function is a number a plus bi that, when plugged in as input, makes the function's output equal 0. The roots of a polynomial p of x are those inputs a plus bi that makes p of a plus bi equal to 0. The techniques for finding zeros apply. The remainder theorem, the factor theorem, and synthetic division, all of these options work well with complex numbers. Let z equal a plus bi. The number z bar is the conjugate of z and is given by a minus bi. The complex conjugate pair a plus bi and a minus bi has an interesting property. Its product is a real number. Z times z bar equals a plus bi times a minus bi. Then you use FOIL and you get a squared minus abi plus abi minus b squared I squared. These cancel out, giving us a squared minus b squared times -1 because I squared is -1. Therefore, we end up with a squared plus b squared plus 0i. This is a real number. Complex conjugate root theorem. If the polynomial p of x has rational coefficients, and if a plus bi is a root with a and b real numbers, then its complex conjugate a minus bi is also a root of p. The fundamental theorem of algebra. Every polynomial of degree n with complex coefficients has at least one distinct root in the complex numbers. If taking repeated roots into account, i.e. multiplicity, every polynomial of degree n with complex coefficients has exactly n roots in the complex numbers. Note, a rigorous proof of the FTA requires advanced mathematics, and it is typically presented in a university-level algebra class. There are many versions of the fundamental theorem of algebra, and the one presented here in 2 parts captures the important points. At the pre-calculus level, we focus attention to polynomials with real coefficients. It was Gauss who was credited with the first proof in his doctoral thesis in 1799. Write a formula for a polynomial using the zeros from the graph and a point away from the x-axis. So given the 4th degree polynomial p of x, fill in the table to organize the data. The goal is to look at the graph to determine the zeros and multiplicities and identify a point away from the x-axis which will help us determine the k value. First, we look at our 0 over here, -4, and we see that the graph goes straight through the point. That means that the multiplicity is 1. We go over to our next 0, and the graph, once again, goes right through the point, through the x-axis, so we have a multiplicity of 1. Here, we have our third 0, and it bounces right off of the x-axis, which means we have an even multiplicity. In this case, it's 2. Since this is a 4th degree polynomial, the multiplicities are going to add up to 4. So 1 plus 1 plus 2 is 4. And then we have our y-intercept here at 0, 32. So we have x minus 2 squared, since this is our 0, 2, this becomes x minus 2, and we have this squared because the multiplicity is 2. Then we have x plus 4 because we have x minus -4, which is x plus 4, and we don't have any exponents since the multiplicity is 1. And then we have x minus negative 1, which is x plus 1 here. We put the k out front, and then we are going to plug in 0 for x, and then set it equal to 32. So you solve, and we see that k equals 2. So we have our equation here, and we just plug in 2 for k, and that is our polynomial. Write a polynomial with real integer coefficients if its zeros include -1, 2i, and the square root of 2. Hint: determine the degree of the polynomial. This polynomial function will have a fifth degree due to the complex conjugate theorem and square root properties. It requires us to have 2i and -2i, the square root of 2 and negative square root of 2, and -1. So here we can see how we have written out the 0 for -1, -2i, +2i, minus the square root of 2, and +square root of 2. And so then we can condense it to this form here.